Okay, in this video we're going to take a look at some problems from section 4.1. First up, number 24. If A is equal to B, then the kite shown is a rhombus. So then rhombus. Squeeze that in there. Well, what we need to know is decide if the statement is true or false. Well, if A is equal to B, then that would mean that all sides are equal. Which is the definition of a rhombus. So that means that the statement is true. Next, we need to take a look at the converse and decide if the converse is true or false. The converse would be if it's a rhombus, then A is equal to B. This side right here is the same length as that side. That's true from the definition of a rhombus. All sides equal. If it's a rhombus, that means that all sides are equal, which means that A is equal to B, so it's also true. And then finally, we have to close this with a biconditional statement, that is to say, rewrite it. And that statement would be A is equal to B if and only if, sometimes abbreviated IFF, it's a rhombus. Or, instead of if and only if, you could use a bijective arrow, like so. Okay, next problem we want to take a look at is number 25. Okay, triangle has sides lengths 3, 4, and 5, then it is a right triangle. So the sides are 3, 4, and 5. That implies it's a right triangle. Well, we'll test this by using the Pythagorean theorem. 3 squared plus 4 squared equals 5 squared. We'll see if this statement is true. 9 plus 16 equals 25. Yeah, that checks out. So all of this implies that this statement is true. Okay, next we need to look at the converse of it. The converse would be if it's a right triangle, that implies that the sides are 3, 4, and 5 units long. False. How do we show something like this is false? We come up with a counter example. 1 squared plus 1 squared is equal to the square root of 2 squared. 1 plus 1 is equal to 2. So all this means that the statement is false. Okay, that was questions 24 and 25. I had one more question I wanted to take a look at. Let me pause and bring that up. And we're back. For question number 45, we need to justify each step in this proof. And the question is, given triangle PQR with a right angle at R, prove that angle P and Q are complementary. Complementary meaning that they add to 90 degrees. And the steps we're given are these 6. And we're asked to provide reasons for it. The first one is PQR is a right triangle. Reason for that is very simple, given. That's part of the hypothesis. PQR is a right triangle. Next one, P plus Q plus R is equal to 180 degrees. What's the reasoning behind that? 180 degrees in a triangle. Next, angle R is 90 degrees. Again, that was given. The hypothesis says that there's a right angle at R, so that was given to us. Next, we have P plus Q plus 90 degrees is equal to 180. Why is this true? Because R is equal to 90 degrees. And it's substitution. Next, P plus Q is equal to 90 degrees. We subtracted 90 degrees from both sides of the equation in step 4. So algebra subtraction, however you want to state that, subtraction works just fine. Finally, P and Q are complementary. That's the definition. And that's what we're looking for in that question. This is kind of a common idea behind proofs. You always have to give reasons that things are true. You can't just blindly state, well, of course they're complementary. We need to give a nice, good chain of logic to reach that point. And whenever we have to do a proof, if we can't provide that chain of logic, well, the proof isn't correct. It doesn't matter if everyone thinks that a proof is true. If we can't show that it's true, then we can't assume it's true, then it's not a proof. I may have a theorem that seems correct. Famous ones would be P is not equal to NP, which has to do with some solving equations, or I'll just write it out right here. For all integers n greater than 3, there do not exist integers or natural numbers a, b, and c such that that is true. This was a very long, outstanding proof. Dates back to, excuse me, Fermat. It was called Fermat's last theorem. It was open. No one had a proof for all cases, all n, for hundreds of years. It was finally proved in the late 20th century. Very complex, very in-depth proof, but it was finally proven. Never mind that up to that point, a lot of people said, yes, it's gotta be true. It's so close to true, but we just can't prove that it's true. And why does that matter? Well, because there might just be some ridiculous little instance where it's true. All it takes is one instance where I can find these numbers A, B, and C and have this equation hold to nullify the entire theorem. Like we did on question number 25, it just takes one counterexample and the whole thing goes away. Okay, and we're going to be dealing a lot with proofs. So, good luck, and until next time, happy geometering.